So here's today's e-learning video for January 27th, 2026. It's pretty small, little assignment there. Or at least it's a small description. Let's make it a little bigger. So we're talking about thermochemistry for e-learning today. And just reminding you from 8th grade science, if you had me for 8th grade science, or maybe it was 7th grade. Might have been 7th grade. I think it was 7th grade, actually. We learned about Newton's law of speed, distance divided by time. Velocity is speed with a direction. That makes it a vector. And acceleration, which is a change in velocity. We could speed up, we could slow down, we could change direction. Any of those, but that would be in meters per second squared, plus or minus. Let's see, right? If it's increasing, it'd be positive. If it's decreasing, it'd be minus. Mass, which is the amount of matter usually measured in kilograms. We might do grams. Today we're going to use grams, but kilograms is part of it. So to accelerate an object with mass requires a force. And for Newton's law, I think it's the second law. Don't quote me on that, but I think it's Newton's second law. F equals ma. Force equals mass times acceleration. So that mass is in kilograms, acceleration in meters per second squared. And that would be the unit we call Newton, named after Sir Isaac Newton, who invented all this stuff and who is to blame for what we know about things like this. At least that's the beginning of it. Einstein had something to say about it later on, trying to change it all, but we never did. I don't think we ever did really change it all. But anyway, so if we apply that force to move an object over a certain amount of, over some distance, then that's the definition of work. Work is force times distance, and of course force was mass times acceleration, and kilograms meters per second squared, which would be a Newton. And distance or displacement is a better term for it. That's what the physicists like, is displacement. That would be in meters. So kilograms meter per second squared times meters would be kilograms meter squared per second squared, which that's what we call a joule, named after James Prescott Joule, who invented something having to do with energy. So joules are an energy unit that we're going to use. And I believe they are the SI unit for energy, which I don't know whether you care about that or not. So let's pretend that you have a piece of iron, a piece of aluminum, a cup of water, and a block of styrofoam, all the same volume, and you left them outside for an hour today. It's pretty chilly out there. After an hour, which will feel colder? They're all going to be the same temperature, but they're going to feel a different temperature, which will feel colder. And then a similar question, the same objects left out in your car on a hot day. Late July, it's all sunny, and it gets about 1 bajillion degrees in your car. And you rub your bare leg against the seatbelt thing, and it like sticks to your leg because it's frozen, or because it's so hot. Same objects in your car on the late day. Which feels the hottest? And probably what you're going to think is that either the iron or the aluminum will be the coldest today and the hottest in the summertime. The styrofoam is going to be the least cold today and the least hot in July. Why? Well, they're made of different materials, and some things move heat better than others. And what we're talking about is specific heat capacity. And the specific heat capacity, here's a definition of that, is the amount of heat energy required to raise or lower the temperature of 1 gram of a substance by 1 degree Celsius. So something that heats up and cools off really rapidly, like your metal pieces, will have a small specific heat capacity, and things that take a long time to heat up and cool off, like water and styrofoam, will have a much higher heat capacity. In fact, the styrofoam, I think, is around 2,000 joules per gram degrees Celsius, if I'm not confused. And I probably am confused, but that sounds about right. Let me see. I wrote that down. Oh, 1,300, sorry. Water's about 4, a little more than 4. Iron's about 0.4. So the smaller the number, the quicker it heats up and cools off. That's why we don't like to cook things in styrofoam. Symbolized by the letter C, the units are joules per gram degrees Celsius. So here we go, C, which is heat over mass and temperature, right? Joules, grams, Celsius. So C also equals, we use Q for heat. For some reason, we use lowercase q. I don't know why. It's just what we use. Q equals m over delta T. That would be the equation for C. And of course, delta T is a change in temperature. We usually go final minus initial. So if it goes up, if the temperature goes up, then your final temperature is bigger than the initial. It's a positive. Delta T is positive. If temperature goes down, then the final temperature is less than the starting temperature, and it would be a negative value for delta T. So Q should have a sign either positive or negative, depending on whether the temperature went up or down. By the way, heat, I'll give you a definition of heat. Energy that flows between two objects because of a difference in temperature. And heat always goes from the warmer to the cooler object. So we can use this equation, C equals Q over M delta T, or rearrange. Some people like this one better because it's all in one line. Q equals MC delta T. And you can solve for any of those. We solved for C here. If we solved for M, it would be Q over C delta T, right? See how that works? And if we wanted delta T, that would be Q over MC. So all that, you can do any of those. As the case may be, we use those to solve heat flow problems. Heat's going from one object to another, right? Typically they're touching, but they don't have to be. Examples, so 250 milliliters of water, that's from a video you're also going to watch, which a milliliter of water weighs a gram, so 250 grams of water from 20 to 100 degrees Celsius, which is what I did on the stove. The C for water is 4.18 joules per gram degree Celsius. How much heat? We're trying to find out how much heat or Q. So go Q equals MC delta T, 250 grams, that's mass, 4.18 joules per gram degree Celsius, that's your C, or specific heat capacity, and 100 minus 20 is your temperature change. So 250 times 4.18 times 80, and I got 83,600 joules, which is an awful lot of joules. I could make it kilojoules and call it 83.6. Right, there's 1,000 joules in a kilojoule, so we'll divide the joules by 1,000 to get kilojoules. Right, so your assignment is going to be problems like this, but you may have to solve for the other variables, not just Q or C. It is 8:57 as I'm finishing this up. I'll try to get it on YouTube and get it posted to Google Classroom ASAP. So hopefully by the next 5 minutes or so, it'll be on. But by the time you see this, it'll already be on, and this is a waste of time. So maybe we'll see you tomorrow. Maybe we won't.